Hey everyone, welcome to 3.1, and this is the next chapter. We're talking more about derivatives. We're not getting away from them. We're talking about extrema on an interval is the first section. Why do we even need to know what extrema are? I don't even know what they are. What is a critical number? What's all this stuff? What do we need to know? Why do we need to know it? A couple of reasons. One, the AP test says this is something you need to know. It's really important. And also, if you work for a company, they're going to say you need to know this as well because we're trying to make a profit here, and we're trying to make as much money as we can. So when is the point where we're going to make the most money before we start not making as much profit anymore? How many do we need to sell in order to make the most money? Or they might say, how many containers do we need? What's the surface area of the container that we have that's going to make this shipping a little bit easier, a little bit better? How can we reduce the amount of waste that we have? What are some things we can do to either maximize our profit or minimize our waste? That way we have as much money as possible. And this kind of stuff kind of answers that. So what we're going to try and do is kind of use this with some functions, and then we're going to get into solving some equations. So let's talk about extrema. Let's get into this. Extrema on an interval. Lots of effort goes into looking at an interval. Does it have a maximum? Where is this maximum? Does it have a minimum? Where is this minimum? It may or may not have either of them. When is it increasing? When is it decreasing? Those are all things that we're going to need to know. We'll talk about concave up, concave down, inflection points, critical points, relative extrema, maximums, minimums, local mins, local maxes, absolute mins, absolute maxes. Holy cow, Mr. Bartman, just stop what you're doing. Okay, let's just slow down and let's talk about definitions of extrema. Definition of extrema. Let f be defined on an interval I containing c. So we have this interval right here, including our endpoints, and we're saying c is somewhere in the middle. We don't know exactly where. So we can say f of c is the minimum. So it's going to be like the y values up and down are going to be our minimum or maximum if f of c is less than or equal to f of x for all x in I. So we have some x in here, we plug it in, and we get some smallest number. That's going to be our minimum. And I bet you can find the next one for the maximum. F of c is the maximum of f on this interval I if f of c is blank for all x in I. You'll come back with this in class, and I bet you'll be able to tell me the right answer. I'm not going to fill it in for you. I bet you can tell me, but it is important you know that part. Okay, and then we say the min and max, the minimum and maximum. If I say min, you know that's actually going to be minimum. I'm just going to be lazy and not write min and mum. I'm just going to write min. So the min and max of a function on an interval are the extreme values. Or if you want to sound cool, you say extrema. Yep, sound as cool as me. Say it now. Extrema. Nice job. Okay, so we could also call this the absolute max or the absolute min. That means they're the highest point the graph ever gets or the lowest point the graph ever gets. No matter how far out we go, if we go all the way out to infinity, it maybe only goes to a certain spot. Okay, so that's the idea of maximum and minimum. Our first theorem, theorem 3.1, is actually an existence theorem, kind of like the IVT. If you remember IVT, we said there's going to be a point in this interval. We don't know where it is, we don't know what it is, but we know there's going to be a point. And theorem 3.1 kind of says the same idea. But the nice thing is, it's really easy. Okay, so theorem 3.1, if f is continuous on a closed interval, AB, which means it's in between A and B, then f has both a minimum and maximum on that interval. Yeah, okay, so there's a minimum and a maximum. Great. So now what we have is the minimum may be the same as the maximum. We don't know, but it could be the same. That's all right. If we have like a horizontal line, the minimum and the maximum would be the same. If we have anything that's not a horizontal line, we're going to have some sort of minimum, some sort of maximum. Okay? Good. Now, let's go on and continue. Let's say we just have a relative max and a relative min. All right? Relative means that if I look at this cubic function, for example, I can keep on going down forever. Great. I can keep on going up forever. So is there actually a minimum? No. Is there actually a maximum? No. But we can say this is the point we really want to look at, and this is the point we really want to look at. So we call them relative mins and relative maxes because they're the ones that are kind of important. We say, I don't care about this part, and I don't really care about that part. I know it's going to go on forever. We're looking at the interval that's right here. All right? So that's what we're going to really look at. And those are kind of arbitrary numbers. We're going to say relative min and relative max. Okay? And those relative min and relative max points are what we're going to be looking at. And let's just take a look at a few of them here right now. There we are. Okay, so here's the first one that I have. Y equals 2x squared plus 1. And here's my interval. Let's just look at the interval. We're going from negative 10 to 10. Does it have a maximum? Does it have a minimum? Does it have either? Does it have neither? Well, we know from that theorem 1.1, it's got to have both a max and a min. Right? So first, what's our minimum value? Well, that's pretty easy. I think I can find that. I'm trying to find the lowest point, which is right there, 0, 1. So there's our minimum. If we go up, what's our maximum? Well, our maximum is going to be this point that's right here. It doesn't really show what it is. Unfortunately, we can't say. But this would be our highest point, and also this would be our highest point of if we have this whole thing. Now, technically, if we're talking about a min and max from negative 10 to positive 10, I should have to zoom out until we get all the way, or I should say zoom up all the way, but that's going to take a really long time, so I'm not going to worry about that too much. Okay, so our min and max, let's just say our min and max from here. Hold on. Alright, there we go. Now we're back. Now let's look at this a little bit better way. I kind of had that messed up. Sorry. First mistake I've ever made. Alright. So, negative 2 to positive 2. Now, I just kind of zoomed in. Alright. So, in my interval, negative 2 to positive 2, my minimum is still 0, 1. But now my maximum, the highest point that I get is right here. Negative 2, 9. Right? And if I go the other side, I'm just going to move this over just a little bit. So if I go 2 right here, this is also 2, 9. So my minimum is going to be 0, 1, and my maximum is going to be negative 2, 9 and positive 2, 9. They're the same thing because the maximum height is the exact same for both sides. So it's symmetrical for a quadratic. Okay, so there's one. And I just want you to notice, what's the slope at this minimum point? Think about it. We'll come back to it. Alright, let's look at this next one. Here is a graph, and I'm going to reset this real quick. Let's take a look. Alright, there we go. This is really going well for me. I'm doing great. Just hang along with me. I know what I'm talking about here. Okay, so now let's look at this graph. This is y equals x cubed plus 3x squared minus 2. Alright, so we can say what's the minimum maximum? Well, I could say the minimum is all the way down here, but we're going to talk about the relative minimum and relative maximum. Okay, so the relative maximum is going to be this point, because I know that this graph, if I keep going down to the left, it's going to keep on going down. If I go to the right, it's going to keep on going up. So the relative min and relative max are going to be these 2 points. Right here's my relative max, negative 2, 2. And right here's my relative min, 0, negative 2. What I want you to look at again is, what's the slope at this point? What's the derivative at this point? What's the derivative at this point? Interesting. Okay, let's look at sine of 0.8. Okay, so we look at this and say, what is the min and what is the max? If you know, if you remember sine, we know that sine does have kind of a max and min. And I'm going to look at my minimum is got to be the lowest point right here, and that's going to be what? Negative 5 pi over 8, comma negative 1, and my maximum is going to be 5 pi over 8, comma 1. Right? My maximum is going to be 1, my minimum is going to be negative 1. Now this time it's not relative because you know the maximum the sine can get is right at, let's see if I can get, the maximum y I can get, I'm right on top of it, right? It's right there, up there. See, that's the max I can get is 1. And then the minimum I can get is down here at negative 1, right? So that's going to be an absolute max and an absolute min because we know that it's only can get as high as 1 and as low as negative 1. All right, so these would be relative minimums and maximums, but they're also absolute minimums and maximums. And what do you think the slope is at this point? What's the slope at this maximum? I wonder if there's something about that we can use. Hey, there is. Okay, let's talk about critical numbers. Critical numbers are going to be critical in finding specific maximums and minimums and all that kind of stuff. So let's figure out what critical numbers are. They are the extrema plus some other stuff. All right, so let f be defined at c. If that means that it's actually got a spot there, it's kind of like it's continuous at c. We don't have a hole or an asymptote or something like that. So if f prime of c equals 0, or if f prime is undefined at c, then c is a critical number of f. All right. And then theorem 3.2, relative extrema occur only at critical numbers. So critical numbers happen when one of two things happens. 1, the derivative is 0, so the slope is 0, or 2, there is no derivative. It's undefined. Okay? That's what we need to know. So there you go. Let's just do a couple of guidelines. I've got one example, and then I've got your assignment. I know this might get a little long, but not too bad. We're okay. Okay, so here are the guidelines. Find the extrema on a continuous function f on a closed interval. We want to find the actual numbers, and we can't just use decimals to say it's 1 and -1. We actually have to find them this time. Okay, on an interval, we may not know what it even looks like. Okay, so here's what we have to do. Find the critical numbers of f in here, right, not including a or b. Evaluate f at those critical numbers that we found, and then evaluate at the endpoints. And the least number of all of these is the minimum, the greatest number is the maximum. So the endpoint might be the minimum, the endpoint might be the maximum, some of these numbers might be the minimum or maximum. Okay, so here's our example. Find the extrema of f of x equals 3x to the fourth minus 4x to the third on the interval -1 to 2. And remember, that is both x values. So we're going from -1 to +2. Okay, so I want to find the critical numbers. Finding critical numbers, remember, that's when the derivative is equal to 0. So what I'm going to do is I'm going to find f prime of x. And we know that's going to be 12x to the third minus 12x squared. Right? But we know that's when the slope is 0. Slope is derivative, so that means I can put in a 0 equals 12x cubed minus 12x squared. Right? So now let's factor everything as much as we can. That's going to be 12 and 12 and x squared, so I can take a 12x squared, and I'm left with an x minus 1. Okay, so from this one, that means that x is going to equal either plus or minus 0, and I take the square root, which is going to be 0. And this one, x is going to equal 1. Right? Plus or minus 0, I don't have anything, but I have 1, 2, 3, and I'm only going to get 3 numbers, right? Because the fundamental theorem of algebra says I can have at most 3 solutions. So I have 0 and 1 as my solutions. All right. So now I have critical numbers are 0 and 1, and I also now have to check -1 and 2 into my original equation up there. Okay. So let's plug them all in. If I plug in 0, so f of 0 equals 0. Right. Put 0 in for x's, I get nothing. F of 1. Put in 1. 1, 3 minus 4 should be -1. Okay. What about f of -1? -1 to the fourth is going to be +1 times 3 is going to be 3. -1 to the third is -1 times 4 is -4, so it's going to be 3 minus -4, and that is going to equal 7. And then at f of 2, I put in 2. 2 to the fourth. 2 times 2 is 4, times 2 is 8, times 2 is 16, times 3, 30 plus 18 is 48, minus 2 to the third is 2 times 2 times 2, which is 8, times 4 is 32. And so that's going to be 48 minus 32, 16. There we go. So, what's the greatest of these? Right there. And what's the smallest of these? Right there. So my max equals 16, and my min equals -1. Sorry, you can't see that. There we go. My max is 16. My min is -1. So we're only worried about the y values. All right? So we found the critical numbers by finding the derivative, set it equal to 0. Find these numbers. Remember when we did that a lot in trig? Yeah, this is the reason why. Now we can do all this stuff and say, oh, I can do this no problem. Set it equal to 0. We got these two numbers, and then these two were from our the interval endpoints, right? So we have to use the endpoints as well because they may be our extrema on this interval. So one of them was from our derivative, one of them was from our endpoint. Okay, there you go. So then here is your assignment to bring back to class the next time I see you, and that is find the extrema of f of x equals x cubed minus 12 on the interval from 0 to 4. Okay, go back and watch if you don't remember how to do it, because this should be fairly simple for you. Good luck.